Welcome! In this video, we will discuss how to implement the software that will control our water temperature device. The hardware is already built, we have created the CubeMX project too, moreover, we have added the needed drivers for the project. Now it's time to delve into high-level programming.
When the program is started, the init task is started first by the operating system, whose function is to perform the basic settings in the application layer. There are still initializations in the main functions, such as the mx gpio init, mx adc1 init, and others, but they operate at a low level, while we perform a higher level reset to default in this task.
Let's take a look at the implementation of this. In the application src init-task.c file, we find the start init task function that implements this task, so FreeRTOS will start this function first. You can see that it starts with initializing the OLED display by calling the OLED init function. This function has formerly been called as well, but within the main function. This has been reorganized and is no longer called by the main function, but by a task created for this purpose.
In addition, the function motor_init, already known from the chapter on motors, is called, as well as two other initialization functions. RTC time setup init and water flow setup init, which will be introduced later. For now, all we have to know is that they prepare the screens for setting the time and the flow rate. As we've seen, the analog to digital converter will do its job continuously and autonomously, but we need to start it first, and we'll do that here as well.
The function ends with a vTaskDeleteNull function call. This is used to delete our task. It seems like exiting a program on the computer, so the task will no longer exist in the list of tasks to run and will not be called again. After the initialization is complete, the program starts its intended operation, where the tasks that implement the display, the motor, and the data storage are run in turn.
The ADC and the storage of its measured values operate on interrupts, virtually independently of these tasks. Our initialization task started the ADC with the function call heladc_start_dma. From now on, the ADC will automatically load the measurement results into the ADC values buffer array passed as a parameter, and once both are present, it will call our function heladc conversion completed callback in the adc read.c file. According to the order set in CubeMX, the ADC values buffer 0 element will be the NTC value, and the ADC values buffer 1 element will be the ADC value corresponding to the current position of the potentiometer.
In principle, we could use the raw values produced by the AD converter in our program, thus these two elements of the ADC values buffer array, in which case we would have nothing to do in this callback function, we may not even have to write it. However, there is measurement error in the analog to digital converter, and the analog signals are subject to noise, which means that we will not always get exactly the same value, but the measurement result will vary around the true value with some scattering. Suppose we set the potentiometer to an arbitrary value, say mid-range. The measured digital value is around 2000. If the AD is 12 bits wide, meaning it can range from 0 to 4095. If we let the measurement run and observe the results, we see that it ranges between about 1980 and 2020 at the extreme, but for the most part, we get values around 2000 plus minus 5, and the positive and negative biases are roughly balanced. In order to improve the measurement result, we put in an averaging filter. To be more precise, we put a low-pass filter into this callback function. The new result always has to be calculated with a given weight to the previous result, so by evaluating several results, we move the result towards the supposedly accurate value. The two parameters of the resulting filter are A0 and B0, which can be set in the adc_read.h file, or more precisely one of them, since the sum of the two must always be 1. The results are stored in the global variables ntcval and potval, so that any part of our program can access them.
So the AD converter gives us the measurement results continuously, but before we get to how the rest of the program uses them, we need two more parameters: the flow rate with the valve fully open and the exact time. This can be entered only once. The former is constant, the latter will be automatically incremented by the RTC, and can also be read out at any time. Currently, these setup options were implemented in advance in the files waterflowsetup.c and rtctimesetup.c. But you are able to easily create them yourself after getting this far in the curriculum.
After starting the program, the main screen welcomes the user, where the left and right buttons allow us to switch between menu items, and the OK button allows us to enter or activate the menu item. The Set Water Flow and Set Time menu items allow us to set the parameters already mentioned. In these, the value in question is displayed, the flow rate can be set in liters/minute, separately for the integer and fractional part, while for the time we can set the year, month, day, and hours, minutes, and seconds separately.
Also on the main screen, we can select the control mode, which can be automatic or manual. In automatic mode, the system decides how to intervene with the valve to achieve the set target temperature, while in manual mode we can move the valve with the potentiometer. In this case, we revert to the traditional method and adjust the valve position ourselves, as we would do with the normal tap.
Now comes the substantive part of our program, water temperature control. This task is handled by the control task, which will be implemented in the file controltask.c. Let's open this file. The body of the for loop found inside contains the primary, high-level control of our system, which decides what state the valve should be in according to the mode selected. In the case of automatic control mode, when the control mode value is CM automatic, we must calculate the signals of a control loop, so we determine the error signal, then use it to calculate the intervention signal, and we output it to the intervention unit. In the first step, we must determine the actual temperature from the raw value received from the AD converter and stored in the variable ntcval. To do this, we will need the ntc driver that we just added, and from it, the calculate temperature function, which is used to do just that. Notice that at this level, we don't need to know how to calculate the temperature from the ADC value. We just call this function, and it gives us the temperature in its return value in float type variable in degrees Celsius. Taking this and the set temperature, we get the error signal, which we use to create a simple p-type controller. The output of the controller will be the intervention signal, meaning the required state of the valve, which is stored in the valve state variable.
The value of valve state is interpreted as a percentage. If it is 0%, it means that the valve is fully closed, while if it is 100%, the valve is fully open. Also note that if the difference is too large, you will get a very large error signal and thus a large intervention signal. If we are running cold water and we suddenly increase it to a much higher temperature, the valve will have to be opened very wide to mix in as much hot water as possible, therefore we may get the intervention signal higher than 100%, which we obviously won't be able to physically achieve. When switching from hot to cold, the case is the same. We can get a value of less than 0%, which we'll also not be able to drive. The intervention signal must be limited between 0% and 100%. In manual mode, no control is needed. Only the user set value is applied to the valve. This set value comes from the pot meter and is stored in the potval variable, which is also continuously updated by the AD converter. In this case, all we must do is translate the value in the potval variable, which varies between 0 and 4095, to a value between 0% and 100% in the valve state variable, which will simply be a multiplication operation.
The high-level control loop gave us the required valve state. However, this did not perform the intervention, the motor was not set to the correct angle, we only stored the required value in the valve state variable. The adjustment of the valve is done by a DC motor, but this and the associated control IC cannot interpret such a signal, but can only rotate the motor at a given speed in the given direction. What we need here is not speed control, but position control. Let's assume that the motor is in the 0-degree position, just as you can see on the table. This means that the valve is in a closed state. The plate in the pipe is perpendicular to the longitudinal axis of the pipe, so water cannot flow through it. If this plate is rotated 90 degrees, it will be exactly parallel to the longitudinal axis of the pipe, so water will flow through the cross-section as much as possible. It makes no sense to rotate it any further, as it would then start to close again, and at 180 degrees it would be completely blocked again. In general, the physical design of valves only allows for rotation between 0 and 90 degrees, so this is the range within which we should rotate our motor shaft. This positioning is further aided by an encoder mounted on the motor to measure the shaft rotation.
On our 3D printed valve, there is still a 1:4 ratio between the motor and the valve shaft. So for a 90-degree butterfly valve angle change, the motor shaft has to make 360 degrees, which is one full turn.
So, we need another control loop to adjust the position of the motor shaft. We know that in our case, the motor gear ratio is 1:120, the encoder has 2 channels, and each channel gives 16 pulses per revolution, which for the ratioed side is 120 times 2 times 16, so 3,840 pulses per revolution. We would like to rotate the motor for a complete revolution, so we would like to count 3,840 from the encoder's signals. Let us therefore correspond 0 encoder pulses to 0 degrees and 3,840 pulses to 90 degrees of rotation. Of course, we have used the fact that the encoder can also determine direction thanks to its 2 channels, so if the motor is rotating clockwise, the pulse received will get a positive sign, otherwise we take it into account with a negative sign when monitoring the position. The number of signed pulses given by the encoder is stored in the encoder position act variable in the driver program for the motor.
So if the desired valve state is 0%, then we need to control the motor so that the value of the encoder position act is 0, while in the other extreme condition, when the valve state is 100%, we want the encoder position act value to be 3,840, so the motor makes a full turn. We split the values evenly between the two. For example, we assign 1920 to 50% and so on.
This lower level position control needs to be performed by the motor control task. Fortunately, the motor driver already has a built-in position control option, so all we have to do is call the appropriate function and the driver does its job, rotating the motor in the right direction so that the shaft is set to the desired angle for the desired percentage. Here, a PI-type controller is implemented to ensure that there is no residual error, so we can set the angle of the motor shaft exactly. The already familiar method of combining the error signal generation, intervention signal calculation, and intervention is also done here, and we also keep track of the sum of the error signals due to the I member of the controller.
Once we have the valve control, our system is basically operational. Now we just need to add the extra features, such as saving data to an SD card. It's a good practice not to write every piece of code from nothing, if you have something to work from. As a final example of the previous chapter, which was chapter 23, you created a data collecting application that saved the brightness data measured by the light sensor to the memory card every half second. Let's use this, just modify it a bit. The time should not be written in milliseconds, but in year, month, day, hours, minutes, seconds format, and of course the amount of hot water used should be written in the second column, not the data of the light sensor. The available example code already contains the code that was carried over from the previous chapter. It is located at application source data logger task.c. We have made some modifications to it in advance. We deleted the data logger sensor init function since we don't need to initialize the light sensor, and renamed the data logger write light level function to data logger write data since its function has changed.
Let's see what we need to change in the state machine in the main cycle. From idle mode, we switched to active mode when the user pressed a button. Now, we change this to start logging when we start using water. Since we assume that our program is running continuously 24 hours per day, we only log when something happens. Zero water usage is not logged continuously. Accordingly, the start of the logging should not be tied to the true return value of the button is rising edge detected function, but to the condition that the valve is open, meaning its position is not 0%. Similarly, the logging is not terminated by a button press, but when the valve state returns to 0. In the case of an error, we shouldn't wait for a button press either. We only wait for a specified time, which in this application should be 10 seconds, and then let's try opening the file again.
The data logger mount and data logger close file functions will be fine as they are. They are exactly as we need them. The data logger open file function needs a small modification, since it currently prints a time and light as the header at the beginning of the file. Let's change this according to the new file. So, for example, the name of the two columns can be time and water use in milliliter.
Let's take what we learned about RTC in chapter 16 and read the current time and date. To do this, we can use functions hal_rtc_getTime and hal_rtc_getDate. Note that both functions must be called consecutively and exactly in that order, because the time retrieval function blocks the values of the shadow registers that form a temporary copy of the date and time in the RTC, so that the two consecutive function calls will ensure that the time and date are a pair of values that are certainly coherent.
The control task constantly updates for us how much water has been used, and it can be found in the global variable used water in liters. We want to write out the water use in milliliters so that only the increment is entered in each row, meaning the amount of water used since the previous logged time. Milliliters will be good for us, because we can avoid using fractions, which simplifies our life when using the fprintf function. We could also write out the water use in absolute values. This means the total amount used since the system was switched on, but this would eventually give us quite large numbers. If the total amount is needed, an evaluation program running on a computer or phone will calculate it for the user.
All we have to do is write the appropriate template to the fprintf function in order to write out the data, and then give it the corresponding parameters of the RTC date and RTC time structures one by one, and the amount of water used. Since we would like to write out only the current amount, we need to reset the value of the used water variable to 0 after each new line. We have finished implementing the program. We can now move on to testing.
So-called unit tests are often written for programs. These are tests that are limited to checking the operation of a small part of the program, usually a single function. No such tests have been created here, only the functionality of the whole program is checked in practice.
Let's see what we can do to test the whole program in practice. We probably won't be able to install the development panel next to a shower, but that would probably be the case for the first test of a real project as well, so we need to somehow manage the initial testing at our desk. We can see the OLED display working. Testing won't be a problem. The buttons and the potentiometer are also available, and we can try them. By switching the system to manual mode, we can also test the positional control of the motor. If the potentiometer is rotated between its two end positions, then the valve's axis should also move between the two end positions, which is 0 degrees and 90 degrees. The moment the valve is opened even a little bit, the logging to the SD card starts, so we can test this function as well and check the saved data by plugging the SD card into the computer. The only problem we have is to check the high-level temperature control. We need to create different temperatures based on which the system can complete the temperature control. We can heat the NTC with our hands, but we can only influence it within a few degrees Celsius, which is very little for an application like this. Another solution would be if we replace the NTC with a potentiometer, but we will use another solution now. You can see two mugs in front of me. These contain warm and cold water. You can guess from the colors of the tapes which contains which. If we put the NTC in one of the mugs, the temperature detected by it can easily be changed.
This method is also good for calibration. If we pour an ice water mixture in one of the mugs, then we can almost be sure that we will measure temperature close to 0 degrees Celsius. And if we boil water and pour it in the other mug, and we place our sensor into it, carefully, not to burn ourselves, then we have to measure around 100 degrees Celsius.
We will not calibrate the sensor now. We just want to test the opening and closing of the valve. The panel in front of me already has the finished software uploaded, so the next step of testing is to power it. We'll do that here with this power cord. We plug it into the appropriate socket, and after a little while, we have the main screen on the display. Now the device starts in automatic mode, so you can set the desired temperature. We're going to set it to 40 degrees. The reason behind 40 degrees is because there's a glass of water in here that's about 60 degrees, and in the cold glass there's water around 20 degrees, and 40 degrees is in the middle. So that's probably a good starting point. But let's not start with testing the automatic mode, but with the manual mode. Because then, we can see the two control loops working one by one. We can see right away that the valve has turned to the 0 degrees position because the potentiometer is seemingly on 0%. If we start turning the potmeter, you expect the valve to move to the correct position. At 50%, we saw roughly a 45 degree angle. At 100%, roughly 90 degrees. Because our motor is not a perfect model, it has a bit of friction, and in real life it would happen similarly. If we turn the potentiometer a little bit forward, we can see very nicely that it tracks the position, so most likely our position control is working well, because this control loop is already active at this point. Once we're done with that, the next step is to test the automatic mode. So we are switching to automatic mode. Since we have 40 degrees set in the program, and the sensor is only measuring 23 degrees, this means the hot water valve has to be fully open to heat the water in our shower. So let's simulate the water heating up in our shower. You can see the measured temperature rise, and as soon as it reaches 40 degrees, it starts to turn off the valve. And if we start to cool down the measured temperature, meaning our water during our shower is getting colder again, then around 40 degrees the valve will open, forcing our water to heat up. So basically, we can say, I'm sorry, but I have to unplug the power because it's getting noisy. So we can say that the software we've created is working appropriately. The two control loops are working well also. So basically, we've done a good job.
In this chapter, we wanted to show you in broad terms how the implementation of a project proceeds from conception to first prototype with some, sometimes strong limitations. Further development work would also be needed to have a complete solution that can be applied in real life. Note that in the example, only the amount of hot water was set. The water pressure was assumed to be constant, and the flow rate was assumed to be directly proportional to the angle of the valve. In a real case, purpose-optimized circuits, meaning target hardware, will be produced with waterproof coating and boxing. The eventual commercialization of the product will be preceded by lengthy testing, revision, certification, pre-production, and important additional tasks involving other professional disciplines. A well-functioning machine usually requires an ideal mix of mechanical engineers, electrical engineers, managers, legal experts, marketing experts, a balanced daily schedule, and an adequate amount of sleep.
This was the final episode of the second season of the Crystal Clear Electronics video series. We hope you will work on many more exciting projects in the future, and use the knowledge you have gained. On behalf of the whole team, I wish you good work and good luck. Bye bye.
Bye.